Hello, I am a.c.atkinson.
And I'm Marco Riani.
Today we want to present some further material from our exciting new book about robust statistics through the monitoring approach.
We'd like to talk about how the search detects the outliers during this increase of subset size. The basic idea at step M is to have a set of deletion residuals for the units which do not belong to the subset, and for those units you have the minimum absolute values of these deletion residuals, and then you monitor the absolute value of the minimum deletion residual.
That is the minimum over the observations not included in the subset used in fitting.
The idea is that if the absolute value of this minimum is too large, then the observations, is to be considered as an outlier, as well as all the others that will be included. So this is the first step in which you start including something which is not in agreement with what you already have in the subset. Of course, this statistic must have an envelope using all steps of the for research, and this envelope is constructed using the theory of order statistics. Given that we want to control the overall size of the procedure, and that given that in each step of the search we test for outliers, we have a problem of simultaneity. In the book we have described the procedure which has a size, as we will see in chapter 5, that is very close to the nominal one.
The nominal simultaneous size of this procedure is 1%, and in chapter 5 we use simulation to show that the actual size that you get when analyzing data is very close to this nominal 1%.
In order to illustrate how the procedure works, we start with the well-known example in the literature of robust statistics, which is known as the stars data. We load the star data.
This is a plot of logs to base 10 of the light intensity from the star and the temperature at the surface of the star.
From this plot you can see that there are 4 units that are clear outliers. Moreover, it is not clear whether there are other stars which could be outliers as well. Our automatic procedure for outlier detection, which is based on the minimum deletion residual. You can see that the trajectory of the minimum deletion residual is inside the bands. Then there is a first exceedance here at step 41, an exceedance of the 9% band, but still inside the 99.9% band. Then comes back inside, then goes outside again. Finally, the masking effect, and notice that the final minimum deletion residual is very, very, very small, even close to the 1% envelope. As you can see from the shape of the envelopes of the minimum deletion residual, with the search, you order the observations from those most in agreement with the model to those least in agreement with it. Therefore, it is normal at the end to include the observations that are least in agreement with your model. Therefore, you have to allow the fact that the bands in the final steps increase.
Notice that here the curves, the boundaries, the simulation envelopes, however they're obtained, that we're getting curve up towards the end, they increase towards the end. This is a perfectly standard thing. It isn't a sign of outliers. The outliers will have to be larger than those envelopes in order to be detected or labeled as such.
In order to have a procedure which has a size of the test which is close to the nominal size, it is not enough to have a single exceedance, because it is clear that if you have 100 steps, there will be that one time randomly it goes above the or below the confidence band. What we need is a procedure that we call envelope superimposition. And given that just after 40 we'd add the first exceedance here, then we start in the step where there was the first significant exceedance. And then we have a reduced sample size, an envelope based on the reduced sample size, which in the top left panel is 42. You can see that if you have an envelope based on 42 observations, these curves trend upwards. And then the trajectory that we have is inside these envelopes. Same thing if you add one more unit. They pass from a subset size of 42 to a subset size of 43. Now, when you pass from a subset size of 43 to a subset size of 44, you can see that the trajectory starts going above the 99% envelope. And so we stop. That is, we stop at 43, which is the last step in which the trajectory stays inside the envelope, and we declare 4 units as outliers. Then these 4 units declared as outliers are automatically shown with a red color. Given that these envelopes curve upwards, for ease of interpretation, sometimes it is important to have envelopes that are horizontal, because we are much more used to horizontal envelopes. Therefore, it is necessary to rescale both the trajectories and the envelopes so that they become horizontal. This is the same curve as before, but now seen with horizontal bands.
Now we'll continue with the analysis of the stars data, but with the envelopes transformed to be horizontal. This is done pointwise for each subset size. We see again that we have a large peak at 43. What is the significance of this? Well, instead of looking at the curved envelopes, we can use a set of straight envelopes and behave in exactly the same way. So this is figure 4.4 now of the book, which I think in a way makes it much clearer what is happening. We have a first envelope which is generated for n is equal to 42. Then we add another observation. The trajectory changes. You can see it actually comes down now when n is equal to 43. And then when n is equal to 44, it goes outside the 99% level, which at this part of the search is the critical value. Trajectories in these plots remain the same, although it's very hard to see it. The lines, the positions of the lines, horizontal lines, will be moving slightly, just as in the ordinary usage of the resuperimposition, the curves were moving, changing a little bit in shape and position.
Well, if you analyze them, you see that this peak is very close to the rejection line. On the other hand, here it is less and less. So this is precisely what you were saying.
That is right. The trajectory remains constant and the envelopes are being changed with sample size.
Finally, notice that with this envelope superimposition, we use the symbol n star in order to differentiate it from our sample size, which is n. So, in this example, the peak took place at the end of the search. In this example, therefore, we had a set of outlying units. These units were entering the search in the final step, and so with this envelope superimposition, we were able to find the precise number of outliers. Now, Let us see now another example that we'd like to show is the example of the loyalty cards data. We have transformed our data. See chapter 6 for a detailed analysis of this data, and now look at the trajectory of the minimum deletion residual. It starts going out at a certain point. Finally, it is also important to notice that due to the masking effect, then the trajectory is inside the envelopes. Once again, also here, it is not important the first exceedance, but it is important the first step in which the envelopes based on n star observations do not contain the value of the trajectory of the minimum deletion residual. So here we start with envelope reappearing position as we have seen before, and then we find the first step in which there is an exceedance of the 99% envelope. Here we stop, and then here our reduced subset size, which is without outliers, is 491. Another example is the bank data. We apply our automatic outlier detection procedure. In this case, the reappearing position involves several steps, and same thing here. We find the value of n star for which there is the first exceedance, and here this first exceedance of the upper envelopes takes place for this value of n star. In all the examples that we have seen so far, the trajectory stays inside and then starts going outside, and then we have the envelope reappearing position. Now we have another example, so-called hospital or surgical unit data, where we observe something which is peculiar, something that we have never seen so far. That is, the envelope starts going out not in the final part of the search, but in the central part. This is a concept that we will exploit a lot in the analysis of regression clustering, and this denotes the presence of two overlapping groups. First, you tend to include the units coming from one group, therefore the reference envelope starts to increase, and this explains why you have an increase in the central part of the search. When the units from the other group start to be included, then there is a decrease.
Because the parameter estimates change and the new units that are coming in no longer seem to be so extreme.
Notice that once again, starting from the end, it is completely impossible to recover the structure based on the two groups. This is the plot that we have seen before of the minimum deletion residual, but this time using horizontal bands. Once again, you can see that there is an exceedance in the central part of the search. We now have to check what is the proportion of the units entering the subset in the different steps. So this is figure 4.31.
These data are taken from a book by Nita, in which they introduce data on logged survival times of 54 patients undergoing liver surgery, together with 4 potential explanatory variables. Later in their book, another 54 observations are introduced to provide an out-of-sample check of the model fitted to the first 54. Their comparison suggests there is no systematic difference between the two groups. We have seen here in our plot that in fact there is a peak somewhere very close to 54 this is a strong suggestion to us that first one group and then the other group are entering. And we can look at this graphically.
So we can monitor the proportion of units that belongs to the first group as a function of the subset size.
Right. After a little random fluctuation, this increases fairly steadily, close to 1, and then it drops back down again to close to a half. Well, in fact, exactly to a half at the end.
Then now let us summarize the conclusions about what the procedure does when there is just a single outlier, when there is a minor proportion of outliers, or when there are two groups of units.
When there is just a single outlier, we would expect that it would enter at the very end of the search and that the trajectory would go along, increasing perhaps slightly with the curving of the envelopes, and then it would just go up by a single step. If, as in the stars data, there is a group of outliers, then they should also come in towards the end of the search. But masking, the changing of the parameters due to inclusion of the outliers in the subset, means, as we saw in the stars data, that the observed trajectory, in fact, decreases again to lie within the envelopes. This is an extremely, one might say, dangerous aspect of data analysis, that towards the end of something, or when all the data are fitted, outliers may be very firmly masked.
On the other hand, finally, the case also very difficult when there are two overlapping groups, for example 60% and 40%, and then as in the hospital data, these two groups do overlap.
Yes. In another part of the book, we describe what we call random forward searches, where the initial subset is chosen at random and a search just as the kind that we've been describing proceeds. And at some point along this way, all of the units in that group will have been included in the subset, and units from one or more other groups will have to start to be included, and there will then be a peak before the outliers take over and change the parameter estimates. We have to do this many times, say 100 starting points, in order to get trajectories that start within each of the groups. So I hope you are convinced that this monitoring of the minimum deletion residuals is an extremely versatile and powerful tool. Thank you very much for your attention.
Thank you for watching.